Okay, so in this video, we want to consider derivatives involving inverse trigonometric functions. We will only consider examples with arc sine of x, arc tan of x, and arc secant of x, because as you remember, the derivative of arc cosine is just the negative of arc sine. The derivative of arc cotangent is also the negative of the derivative of arc tangent, and the derivative of arc cosecant is also the negative of the derivative of arc secant. So really, as far as understanding how to use these rules of differentiation, involving the other three inverse trig functions will not give us anything new. Let's consider with a simple example involving the arcsine function and the chain rule. So what if we asked, so we'll use these three formula of differentiation. What if we asked for the derivative, say, of arcsine of, say, 3x? Well, once again here we have a composition, right? Given x, we would do 3 times x, then take arcsine of this value. So the outside function is arcsine, and we have to differentiate that first. And here's where you have to be careful with the 3x. If you look at the formula for the derivative of arcsine of x, it says the derivative of arcsine of a variable is 1 over the root of 1 minus the variable squared. So here x is the argument, but again x is a variable, so whatever x here is, you have to plug it in here, right? So the derivative of arcsine is 1 over the square root of 1 minus, that's not x squared, it's whatever the argument is, squaring that. So it's 1 over the root of 1 minus the argument squared, and the argument here is 3x. So what goes in here is 3x. But we're not done. We have to multiply what we have so far by the derivative of what's left over. What's left over is 3x. The derivative of that is 3. And now there is nothing left over, so we can rewrite this slightly in a simpler form, but the derivative is over, so we have 3 over the square root of 1 minus, and here you can square this will give you 9x squared. And that's the derivative of arcsine of 3x. Let's go with, say, the derivative of arctangent of x to the 5. So what if we differentiate arctangent of the 5th power of x? Well, once again we have a composition. If I give you an x value, you will first find its 5th power and then take the arctangent of this value. If you look at the formula for the derivative of arctan of x, what you will get is 1 over the argument squared plus 1. And this holds for any variable, so here we have to be careful. We differentiate the outside function, arctangent, and the derivative of arctangent is 1 over the argument squared. Well, here the argument is x to the 5. So it's x to the 5 squared plus 1. And that's a derivative of arctangent of x to the 5, but only of arctangent. There's still the x to the 5 left over. So we have to multiply by the derivative of what's left over. And the derivative of x to the 5 is just 5 x to the 4. There's nothing left over, so the differentiation is over. And we can again simplify this as 5x to the 4 over, and if you square x to the 5, you get x to the 10 plus 1. So there you have it. The derivative of arctangent of x to the 5 is this expression. Let's do one with arcsecant. Let's go with arcsecant, say, of root of x. So the derivative with respect to x of arcsecant of root of x. Well, once again, if you look at the formula for the derivative of arcsecant, At x, you plug in the argument, which is x here, and the argument squared here. So the argument now is root of x, and again we have a composition. If I give you an x value, first find the square root of x, then take the arcsecant of root of x. So the outside function is arcsecant, differentiate that, 1 over the argument, whatever it may be, the argument here is root of x, so root of x, times the square root of the argument squared plus 1, and here the argument again is root of x. But that's just the derivative of arcsecant. There's a root of x left over, so times the derivative of root of x, and this is, as you know, 1 over 2 root of x. Now there's nothing left over. We're done with the differentiation. We can simplify. We have a single 1 on the numerator over 2. And if you look here, we have root of x times root of x. That's just x. And then we have the leftover root here. And if you look, we have the root of x squared, but that's just x. So you're left with the root of x plus 1. And that's a derivative of arcsecant of root of x. Let's throw in there some exponential and logarithmic functions. What if we wanted the derivative, say, of 3 to the arctangent of x squared? Well, here again we have a composition, but now two compositions. If I give you an x value, you first have to square it, then take the arctangent of it, and then raise 3 to this power. So the last function that we would compute would be raising 3 to this exponent, so it's the exponential function base 3. If you remember, the derivative of an exponential function is the function itself times the natural logarithm ln of the base, which here is 3. But that's just the derivative of the exponential function base 3. We still have to multiply what we have so far by the derivative of what's left over, and that is arctan of x squared. Remember that the derivative of arctangent is 1 over the argument squared plus 1. So here we'll have times 1 over the argument squared, x squared squared is x to the 4, plus 1. That takes care of the arctangent times the derivative of what's left over. What's left over is x squared. The derivative of x squared is 2x. And that is now the derivative of this function, is this function. We can write this in a slightly nicer form by regrouping as a single fraction. We'll have 2 ln of 3, so the constant terms first, times x, times 3 to the arctangent of x squared, the whole thing divided by x to the 4 plus 1. So there you have it. What if we had, say, a logarithmic function? Let's go with the derivative of ln of, say, arcsine of 2x. So derivative of the ln of arcsine of 2x. Once again, here we have two compositions. If I give you a value of 2, multiply a value of x, multiply by 2, then take the arcsine of it, then take the ln of the whole thing. So the outside function is ln, and if you remember, this is the natural logarithm, right? The logarithm base e. The derivative of ln is 1 over its argument. So we'll have 1 over the arcsine of 2x times the derivative of whatever is left over. Well, this is arcsine of 2x. The outside function is arcsine. The derivative of arcsine, if you remember, is 1 over the root of 1 minus the argument squared. And the argument here is 2x. There's still 2x left over, so times the derivative of 2x, which is simply 2. And now we have the derivative. Let's simplify a little bit. On top we have a 2 over arcsine of 2x times the root of 1 minus, and if you square this you'll get 4x squared. And there you have it. So this is how you use the rules of differentiation for inverse trig functions in the context of differentiation. Now, one question is, what if we have, and again, if you had, say, a product or a quotient, you would use, of course, the product and quotient rule. Let's do one more example, or at least two more, where one we have a product, where in the other we have a quotient of two functions. What if we asked for the derivative, say, of x cubed times arctangent of, say, x squared? Well, we have a product between x cubed and arctangent of x squared. So we use the product rule, which says that the derivative is of the product is the derivative of the first function, which is 3x squared, times the second function, arctangent of x squared, plus the first function, x cubed, times the derivative of arctangent of x squared. And here, be careful, we have a composition. If I give you an x value, you will first square it and then take the arctangent of x squared. So we differentiate first the arctangent function. The derivative of arctan is 1 over the argument squared plus 1 times the derivative of x squared, which is 2x. Well, let's simplify the expression. We have a sum of two terms, and if you look, we have a common factor of x squared. There's 3 here, there's 2 here. We can factor in x squared. And if we do, we're left here with a 3 arctan of x squared plus, if we factored x squared from x cubed, that leaves us with a single x, times x, therefore 2x squared on the numerator, over x squared squared is x to the 4, plus 1. So there you have it, the derivative of x cubed times the arctangent of x squared. And if you have, of course, a quotient, you use the quotient rule. Suppose we have the derivative, let's throw in an arcsecant. Let's go with arcsecant of x over x. We have a quotient, so we use the quotient rule, which has the derivative of the first function, which is 1 over x root of x squared minus 1, times the second function times x, minus the first function, arcsecant of x, times the derivative of the second function, which is simply 1, all over the denominator all squared, x squared. Well, we can simplify as always. We have an x over an x here, so both of these cancel. And that will give us 1 over root of x squared minus 1 minus arcsecant of x over x squared. And here you have an option. You can either split the two up, or you can leave them as a single fraction. I will split them up here. So if I have 1 over root of x squared minus 1 divided by x squared, if you divide by x squared, same as multiplying by 1 over x squared. So we'll have 1 over x squared root of x squared minus 1 minus arcsecant over x squared. And again here, if you want, you can factor a 1 over x squared. And that will give you 1 over x squared times 1 over root of x squared minus 1 minus the arc secant function of x. Let's do one last example now, where we have the derivative of a trigonometric function of an inverse trigonometric function. And we'll see that every time we have in our final answer a trig function of an inverse trig function, we can always simplify using the idea of Pythagoras' theorem and building a right triangle. So let's consider an example of this. And this will be our last example for this video. Suppose we ask for the derivative of sine, say, of arctangent, say, of x, some power of x. Let's go with x to the 4. Once again, we have here two compositions. If I give you an x value, first take its fourth power, then take the arctangent of this value, then take the sine of this value. Let's differentiate using the chain rule, and then we will try and simplify and get rid of the trig and inverse trigonometric functions. So, the outside function is sine. The derivative of sine is cosine. Cosine of what? Of whatever is left over. So cosine of arc tangent of x to the 4 times the derivative of what's left over. The outside function is arctangent. The derivative of arctangent is 1 over the argument squared plus 1. The argument here is x to the 4. So there you go. Times the derivative of what's left over, x to the 4. The derivative of that is 4x cubed. So let's now rewrite this. We'll have 4x cubed over x to the 8 plus 1. Times the cosine of the arctangent of x to the 4. Now, as far as the differentiation goes, we're done, right? There's nothing left over. So the derivative of sine of arctangent of x to the 4 is 4x cubed over x to the 8 plus 1 times the cosine of arctangent of of x to the 4. I think that we can simplify this greatly. Every time you're left in the end with a trigonometric function of an inverse trigonometric function, you can always simplify a great deal. All we have to remember is, well, what is an inverse trig function? If you recall, a trig function takes an angle and gives a ratio of sides. Therefore, an inverse trig function takes a ratio of sides and gives you an angle. So an inverse trigonometric function of anything is always an angle. Let's call this theta. So all we want here is to know what's cosine of theta. Well, if you think of it, theta is arctangent of x to the 4, right? So theta is the arctangent of x to the 4. If you want to get rid of the inverse trig function, take tangent on both sides. So tangent of theta equals tangent of arctangent but tangent is the inverse of arctangent, so it cancels arctangent, and we're left with, on the left, tangent of theta is quite simply x to the 4. Remember now that tangent, if you think of your trig SOHCAHTOA, is the opposite side over the adjacent. And now we can build a right triangle where the angle is theta, right? So if you build a right triangle, The angle is theta. And now, well, if you think of it, let's write this as a fraction. X to the 4 is just x to the 4 over 1. So, tangent of theta is the opposite side over the adjacent. Well, the opposite side we can take to be x to the 4 over the adjacent side, which is 1. And once again, we can complete this right triangle using Pythagoras' theorem. We want the hypotenuse, call that c. And by Pythagoras' theorem, we know that the base of the triangle squared plus the height of the triangle squared, if you square x to the 4, you get x to the 8, equals the hypotenuse squared. This is positive, and so we can easily solve for c by taking the square root of this. So c is the square root of x to the 8 plus 1 squared, which is just 1. And we have the hypotenuse of our right triangle, the root of x to the 8 plus 1. And now we have a complete triangle. We have the angle, we have the adjacent is 1, the height is x squared, x to the 4, and the hypotenuse is the root of x to the 8 plus 1. And so now we can solve for our cosine of theta. If you remember, cosine, so SOHCAHTOA, cosine CAH, is the adjacent side, 1, over the hypotenuse, the root of x to the 8 plus 1. Which we can write, if you want, as 1 over x to the 8 plus 1 to the power of 1/2. And now we can replace in our final answer. You see, instead of having this rather complicated expression, cosine of arctangent of x to the 4, it's the same as 1 over x to the 8 plus 1 to the power of 1/2. So you see we're able to simplify this and get rid of the trig function and the inverse trig function altogether. So what is our final answer then? Our derivative, dy over dx, was equal to, let's write the first part, 4x cubed over x to the 8 plus 1 times cosine of theta, but cosine of theta is just 1 over x to the 8 plus 1 to the power of 1/2. So times 1 over x to the 8 plus 1 to the power of 1/2. And we can once again simplify as a single fraction. The numerator will be 4x cubed times 1, which is 4x cubed, over, well, the power here of x to the 8 plus 1 is just 1. So when you multiply the same base, namely x to the 8 plus 1, you add the exponents. So x to the 8 plus 1 to the exponent 1 plus 1/2, but 1 plus 1/2 is 3/2. And there you have it. And you can appreciate the simplicity of the answer given the original function. Right? The function was originally sine of arctangent of x to the 4. So we have a trig function of an inverse trig function, and somehow the derivative does not contain any trig or inverse trig function. And this is not a coincidence. It will always happen. Every time you differentiate a trig function of an inverse trig function, you can always use the idea that an inverse trig function is an angle, then build a complete right triangle, and from this you can always simplify the answer so that in the end you have no trig function or inverse trigonometric function.